In this presentation, we focus on the Dynamic Berth Allocation Problem, which is the challenge of assigning vessels to berths when arrivals occur over time and schedules are uncertain. Unlike a static plan where all arrivals are known in advance, the dynamic setting forces repeated decisions as new information arrives. This problem matters because berth allocation sets the tempo for the entire terminal. A poor berth plan increases vessel waiting time, reduces berth utilization, and can trigger downstream congestion in cranes, yard operations, and truck gates. The goal is to assign arriving vessels to berths over time under uncertainty. In practice, arrival times shift due to weather delays, upstream port congestion, and schedule adjustments. Operationally, you are balancing three competing pressures at once: minimizing waiting time, choosing berths that offer efficient handling, and meeting service quality agreements with shipping lines. The scenario is Port Metropolis Container Terminal. The terminal handles more than 2,000 vessel calls annually across 12 discrete berths. Vessels range from 1,000 20-foot equivalent unit feeder ships to 24,000 20-foot equivalent unit, ultra-large vessels. The key operational point is heterogeneity. Vessel sizes, berth capabilities, and crane availability differ, so the best berth is not the same for every vessel. This slide summarizes berth capability tiers. Berths 1 to 3 accommodate vessels up to 8,000 20-foot equivalent units and have 3 quay cranes each. Berths 4 to 8 handle mid-size vessels up to 15,000 20-foot equivalent units with 4 to 5 cranes. Berths 9 to 12 are dedicated to ultra-large vessels with 6 to 8 high-productivity cranes, meaning they can process big ships faster but are scarcer resources. During peak season, the terminal may see 15 to 20 vessels arrive within 48 hours. Each vessel has draft requirements, handling time expectations, and departure deadlines. This forces real-time trade-offs. Assigning a vessel immediately to a suboptimal berth can reduce short-term waiting, but it can increase processing time and block a future high-priority arrival. We will solve the problem using multiple tiers. Tier 1 is a complete integer programming formulation that defines the baseline optimization model. Tier 2 is an earliest deadline first heuristic for fast feasible decisions. Tier 3 uses a genetic algorithm for global search. Tier 4 uses reinforcement learning with a deep queue network to learn a policy. Tier 5 integrates the decision into a digital twin. Tier 7 adds a human and artificial intelligence partnership for robustness under exceptions. Tier 1 defines a complete integer programming model for dynamic berth allocation. The core decision is when a vessel starts service at a given berth. This tier is important because it makes all constraints explicit. Even if you later deploy a heuristic or a learned policy, the Tier 1 model defines feasibility and cost in a precise way. This slide defines the three main sets: vessels, berths, and discrete time periods in the planning horizon. Operationally, these sets define the scope of the problem instance. The time discretization is a modeling choice that trades realism for tractability. This slide defines key inputs. Arrival time specifies when a vessel becomes eligible for service. Processing time depends on both vessel and berth, reflecting crane differences and berth-specific productivity. Desired departure time represents service urgency. Vessel length and berth length capacity enforce physical compatibility. Finally, the waiting weight and handling weight control how strongly the objective penalizes idle time versus service duration. The main decision variable is a binary indicator that equals 1 if a vessel starts service at a particular berth at a particular time. The model also tracks each vessel's actual start time and completion time. Operationally, those derived times are what drive waiting costs, delay risk, and berth occupancy. The objective minimizes a weighted sum of waiting time and handling time across all vessels. Waiting time is the gap between actual start and arrival. Handling time is the gap between completion and start. This structure pushes the plan to start vessels promptly while also choosing berths that process them efficiently. This slide lists the full set of constraints used in the integer program. The model enforces that each vessel is assigned exactly once. Berth usage is limited. Start and completion times are computed consistently. Service cannot begin before arrival. Berth length compatibility is satisfied, and vessel service does not overlap at the same berth using an ordering rule. The assignment constraint ensures each vessel is scheduled exactly once across all berths and time periods. Operationally, this prevents missing a vessel, duplicating a vessel, or leaving the plan partially specified. This constraint limits berth usage so that only one vessel is started per berth under the simplified capacity logic given. Operationally, the core idea is that a berth cannot serve two vessels at the same time. Capacity constraints prevent physically impossible overlap. This constraint defines each vessel's actual start time as the weighted sum of time indices selected by the assignment variable. Operationally, it turns a binary schedule choice into a real timestamp that can be used to compute waiting and completion times. This constraint defines completion time as start time plus the processing time at the chosen berth. Operationally, completion time is what determines when the berth becomes free again and whether a vessel risks missing its desired departure. The arrival constraint requires that a vessel's service cannot begin before it arrives. Operationally, this captures the basic reality of dynamic conditions. You can plan ahead, but you cannot physically start service before the ship is at the terminal and ready. The length constraint enforces berth compatibility by requiring that a vessel fits within a berth's length capacity. Operationally, this prevents unsafe or infeasible assignments, such as placing an ultra-large vessel into a berth designed for feeder ships. This slide expresses a non-overlap rule using a big M ordering logic. It ensures that if vessel I is served before vessel K at the same berth, then vessel I must finish before vessel K starts. Operationally, this constraint is essential because it prevents temporal collisions in berth occupancy. It is also a major driver of complexity because it introduces ordering choices between pairs of vessels. This diagram provides a visual representation of dynamic berth allocation with a node-based structure. Use it to connect the math to operations. The diagram helps you see how vessels flow through time, how berths act as constrained resources, and where conflicts occur. This example uses 3 vessels and 2 berths over a 12-hour planning horizon. Vessel 1 arrives at time 0, Vessel 2 arrives at time 2, and Vessel 3 arrives at time 4. One optimal assignment is Vessel 1 on berth 1 from 0 to 4, Vessel 2 on berth 2 from 2 to 6, and Vessel 3 on berth 1 from 4 to 10. The example reports a total service time of 14 hours with 0 waiting time, illustrating how complementary berth choices can eliminate queues. Tier 2 builds a feasible plan quickly by prioritizing vessels with the most urgent departure targets. The heuristic sorts vessels by desired departure time. Then, each vessel is assigned to the berth that minimizes its completion time while respecting feasibility constraints. The operational benefit is speed. You can generate a schedule in real time as arrivals change. This flow diagram shows the logic of the earliest deadline first heuristic, from sorting to berth selection to schedule update. Operationally, the key mechanism is updating berth availability after each assignment. That update is what propagates the impact of early decisions into later feasibility. This slide shows an example of heuristic output, listing berth assignment, start time, completion time, waiting time, and processing time. The example reports a total service time of 32 hours. It also illustrates a common heuristic weakness. A vessel can incur waiting time, such as the reported 3 hours, because greedy choices earlier consumed the best berth windows. This code section defines the vessel and berth entities and shows the solver structure. Operationally, pay attention to how vessels are sorted by desired departure time. That ordering is what makes the method behave like a deadline-driven dispatcher. This section iterates over vessels and chooses a best berth for each vessel. The important operational detail is the feasibility check against berth capacity and berth available time. A correct implementation must never schedule a vessel into a berth window that is already occupied. This section computes the earliest feasible start time as the maximum of vessel arrival time and berth available time, then updates the berth availability. Operationally, that update is the dynamic element. It ensures that once a berth is allocated, downstream decisions reflect the new occupancy. Tier 3 encodes berth allocation plans as chromosomes. Evolution operators explore combinations that greedy heuristics may miss. Constraint violations are handled through repair and penalty terms. The advantage is global search. The algorithm can rearrange multiple vessel assignments simultaneously to reduce bottlenecks. This slide defines a fitness function that increases when waiting time and processing time decrease, and decreases when penalties for constraint violations increase. Operationally, fitness is the scoring rule that guides evolution. If penalties are not calibrated well, the algorithm may prefer infeasible schedules or, conversely, become overly conservative. This diagram illustrates the genetic algorithm cycle: selection of better chromosomes, crossover to combine patterns, mutation to introduce diversity, and repair to restore feasibility. Operationally, repair matters because birth assignment is heavily constrained. Without repair, most random changes would create overlaps or capacity violations. This slide reports typical improvements compared to the earliest deadline first heuristic, described as 15 to 25% reduction in total service time. For the sample problem, the genetic algorithm finds 28 hours total service time compared to 32 hours for the heuristic, which is a 12.5% improvement. This code section outlines how individuals are created as vessel, birth, and start time tuples. Operationally, the chromosome representation must preserve all essential decisions. If start times are not handled consistently, the algorithm can appear to improve fitness while producing unrealistic schedules. This section defines fitness evaluation, including penalties for incomplete assignments, capacity violations, and overlaps. Operationally, the best practice is to penalize violations strongly enough that feasible improvements dominate infeasible shortcuts. This section outlines selection, crossover, and mutation, plus elitism to retain the best individual. Operationally, elitism is useful because it stabilizes progress. It ensures that if a good schedule is found, it is not lost due to random variation in the next generation. Tier 4 learns birth assignment policies through interaction with a simulated environment. The agent observes the current time, birth availability, and which vessels are waiting. At each step, it can assign a waiting vessel to an available berth or choose to wait. This makes the policy adaptive. It can learn that strategic waiting may reduce later congestion. This slide summarizes the state definition, including current time, berth availability information, the waiting queue, vessel features, and historical performance metrics. Operationally, state design determines what the agent can learn. If you omit urgency or vessel size, the policy cannot learn to prioritize correctly. This slide defines the action as selecting a vessel, selecting a berth, and optionally selecting a delay decision. Operationally, this action structure allows the agent to represent both immediate assignments and the decision to defer assignment until a better berth window opens. This slide defines the reward as a negative cost for waiting and processing, plus a positive utilization bonus. Operationally, the utilization bonus discourages leaving berths idle. The waiting and processing costs encourage fast turnaround and low congestion. This diagram shows the deep queue network training loop for dynamic berth allocation. The operational point is that the environment simulates arrivals and berth occupancy, while the agent learns from trial and error. That is how the policy can discover patterns like delaying a low-priority vessel to reserve a high-capability berth. This slide reports that after 500 training episodes, the deep queue network achieves an average total reward of negative 45.2. This outperforms a random policy at negative 127.8 and approaches the genetic algorithm baseline. The slide also notes that the policy learns strategic waiting and high-value assignments. This code section defines the environment state and the waiting queue mechanism. Operationally, the waiting queue update is crucial. If arrivals are not added correctly, the agent will train on an unrealistic decision process. This section constructs the state vector from time, berth remaining time, berth availability flags, and vessel features. Operationally, normalization choices affect learning stability. For example, normalizing vessel size by 1,020-foot equivalent units keeps feature scales comparable. This section implements the step function and defines rewards for valid assignments, waiting, and invalid actions. Operationally, penalty design is what teaches feasibility. A strong penalty for invalid actions pushes the agent away from illegal assignments that violate berth capacity or vessel length constraints. This section defines the deep queue network architecture used to approximate action values. Operationally, the network capacity must match problem complexity. Too small and it cannot learn the interaction patterns. Too large and it may become unstable without enough data. This section defines experience replay, storing transitions and sampling batches for training. Operationally, replay reduces correlation in training data and improves learning stability in non-stationary environments. This section computes targets using a target network and updates the queue network via mean-squared error loss. Operationally, the target network is a stabilizer. Without it, the learning targets move too quickly and the policy can oscillate. This section decays the exploration rate and periodically updates the target network. Operationally, exploration decay is how you shift from learning to execution. Early randomness explores the decision space. Later, the agent commits to the best learned assignment patterns. Tier 5 elevates berth allocation into a full terminal simulation. It synchronizes berth assignment with crane scheduling, yard operations, gate processes, and vessel traffic management. The goal is to evaluate the system-level consequences of berth decisions, such as how a berth choice changes crane contention or yard congestion. This figure shows a system of systems architecture for terminal operations. Operationally, it emphasizes data flow and synchronization. A digital twin is only useful if the digital state remains close enough to the physical state to support reliable what-if decisions. The example reports a twin processing more than 15,000 events daily and maintaining synchronization within 30 seconds. During Typhoon Helena, the system simulated 50 rescheduling scenarios in 2 minutes and identified a strategy that reduced total delay costs by $2.3 million. The plan delayed 3 large vessels by 8 hours while expediting 7 smaller vessels, reducing congestion by 23% and improving berth utilization from 67% to 81%.